Today I'm talking about something that I think is pretty fascinating, which is the game of life. Now, I don't mean the game of life, the board game that you might play as a child, or the game of life that in some sense we're all playing, but rather John Conway's game of life about cellular automata. Now, I expect many people are already familiar with the game of life, so I'm just going to say a brief word about it before I move on to talk about what I'm really going to talk about in this video, which is taking the game of life and making it be able to be played in color, so with different colors, whereas traditionally the game of life is played in black and white. So what is the game of life? Well, you can imagine a grid of cells. And the cells are either alive or dead, and that's represented here, where a dead cell is written as 0 and an alive cell is written as 1. So cells are either alive or dead, and each state of the board or state of the game can produce a subsequent state of the game where cells change their status from live to dead. And how the state of the game produces a subsequent state is according to these rules that relate to the neighbor count of each cell. So every cell is adjacent to some number of living neighbors. And a cell is adjacent to another cell just if the distance to that cell, up, down, forward, or diagonal, up, down, left, right, or diagonal, is 1. So a cell is adjacent to all these cells around it. And then the number of living cells, in this case 2, would be the neighbor count. So you could have between 0 and 8 neighbors. And yeah, that would produce a neighbor count for any cell. This cell in green here has a neighbor count of 2. This cell up here would have a neighbor count of 2, it being adjacent to these two. This cell over here in the lower right would have a neighbor count of just 1, only being adjacent to one living thing. And so what happens is you look up in your rules using the key, the neighbor count, and you find a value, an action, what happens to you. If you have 0 neighbors, you die. If you have 1 neighbor, you die. If you have 2 neighbors, you become alive. So we might call this alive or life. You become alive. So if you, like this cell right here, for example, has 2 neighbors. So in the subsequent state of the game, this cell would be alive, and so on. If you have 3 neighbors, you're going to stay whatever you are. If you were alive, you'll stay alive. If you were dead, you'll stay dead. And then any other number of neighbors is just dead. Die, 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 die. So from these simple rules, John Conway's game of life can produce complex patterns. We can see that here. Let's see. Let me look for a good example. Here's a GIF. Simple rules produce these kind of unpredictable and complicated shapes and repeating patterns and sequences, and they can be quite huge and impressive, very interesting and just amusing to watch. But as you notice, these are simply alive or dead. They're black or white. Black is alive and white is dead. So in my view, that's not ideal. I think we could take the rules of game of life and try to make it in color, try to produce pictures with it. Maybe it would be more interesting. So how I'm going to do this, I think there are many ways to apply the game of life to images, or to take the game of life from black and white into color. But what I'm going to do in this video is talk about a kind of simplistic approach, where what I'm going to do is I'm going to imagine an image as an array of pixels, as a 3-dimensional array. So I'm saying an image is a 3-dimensional array because it has a height, h, it has a width, and it's got a 3rd dimension, color, because each pixel can be broken up into an R, a G, and a B, and red, green, and blue, an RGB. And red, green, and blue are numbers between 0 and 255 that represent a kind of intensity for that number. So yeah, we can imagine our image, if we call our image I, it has three indices or three dimensions that we can look into. So we could say, what is the 0 column, the 0 row, and the first color value? And that would get us a number between 0 and 255. So we think of our image as a three-dimensional array. And because it's got three dimensions, we can play on this three-dimensional array essentially three games of life at once on the same board. We can imagine these three games of life just overlaid one over the other, one for red, one for green, and one for blue. So how we play these games of life is slightly different than what I just showed you, because rather than having a true or false, alive or dead, what we have is a number between 0 and 255. So we will say that a cell is alive if its value is greater than 1/2 of 255. If it's got a value of greater than 1/2 of 255, then we're going to count it as alive. Otherwise, we're going to count it as dead. So this just reduces the complexity of having values between 0 and 255 and kind of turns it into a Boolean alive or dead state, a true or false state. The other thing we need to do to apply the rules of the game of life to an image is consider what it means to be alive, stay, or death. The kind of three actions that any cell in the game of life can undertake in order to generate the subsequent state. So because this is my first attempt and this is kind of a simplified version, what I'm going to do is say alive or life means change the intensity to 255, the max value. Stay is no change, and death is going to take the intensity to 0. So a completely dead cell would be 0, 0, 0, dead on red, dead on green, dead on blue, and that would just look white. So with these rules, and given that we have three boards overlaid on top of each other, what we can do, or rather not what we can do, but what we will produce is up to 8 colors. 0, 0, 0, as I mentioned, is going to give us the color black. Would be able to get red, green, and blue, with just one of these being fully enabled. 110 is going to produce the color yellow. And here I'm saying 110 just to mean, like, really what it is 255, 255. I'm just using 1 because we only have one enabled color. We only have one active color. But yeah, we'll be able to produce purple, teal, and white too. White meaning the cell is alive in all three boards. So we can go between black and white with 8 colors. Let me show you my implementation of this of the project that I've just described. And what I'm going to use is NumPy and the Python image library, or Pillow. NumPy will just let me easily convert images into arrays or data frames. The Python image library, the image will just let me read images from a disk and write them back, which is why I'm using NumPy and Pillow. So what I'm going to do, I'm going to open an image, and I'm just using an image of Donald Trump here. Let me show you that. Here's my starting image of Donald Trump that I'm going to feed into the game of life and see what happens. I'm going to resize it to 256 by 256. The reason for that is computing subsequent states in the game of life can be a bit computationally expensive on larger boards, and we're going to be doing 3 at once. And I didn't optimize this code at all, so it's going to run kind of slowly. And we want to produce a few frames. So we're going to get this output list, which is going to just convert, which is going to call the advance function, which I'll show you in a second, on our input frame. It's going to advance essentially 50 turns in the game of life, and it's going to supply a dictionary of rules. So the rules are going to be what I showed you over here. It's going to be the alive, dead, it's going to be the alive, dead, or staying the same, depending on your neighbor count. And I'm just passing those as an argument because we may want to change the rules or modify them. Yeah. So when we get that output list, we're just going to save it as an animated GIF, 500 milliseconds a frame. Yeah, and we're going to make it loop. So yeah, let me just step through the advance function real quick. These two lines at the beginning are just saving all the x's and y, all the indices into arrays. I just did that because I suppose I think it's slightly faster. There's not really a huge reason to do this, but I just didn't want to call the length function every iteration of every advance function or every next frame function. So yeah, I just stored each of the x and y indices into their own variable. I'm going to accumulate all of my next frames into this results variable. And then what I'm going to do is I'm going to iterate while I is in the range of 0 to n, so the number of frames I want to advance. What I'm going to do is I'm going to add the current frame to the results list, and then I'm going to compute the next frame of the current frame given the x's, the y's, and the rules. And I'm just going to repeat that n times, and then I'm going to return those results. So let's go ahead and look at the next frame function, which is going to, take the x's, the y's, and the rules. The first thing it does is copy the current frame. We don't want to be modifying the current frame because that will, one, I guess modify the current frame, but two, it will change the calculations. So if we say, this cell, if we say like this cell here is going to die because it has a neighbor count of 0. When I compute the neighbor count for this cell, I don't want this cell to already be dead because that's going to change the outcome. If this cell is already dead, like if I was changing the array while I was updating it, then this cell is going to remain dead because it has no neighbors. It only has one neighbor, so it's going to remain dead. Whereas what should happen is when I'm updating this frame, this cell should become alive. It has 2 neighbors, and this cell should die because it only has no neighbors. So, I don't want to be modifying the frame. What I want to do instead is create a duplicate frame that I'm writing everything into. So I can say, okay, here, this cell is going to be alive, this cell is going to be dead, and so on. And then I can just return my duplicate frame. So that's why I have a copied frame there. I'm just going to say for x in x's, the list of x indices, for y in the list of y indices, for color in my list of colors. What I'm going to do is say in the output frame, or in the output NumPy array, at this position, x, y, color, what I want you to do is look up in the rules dictionary the number count, the key being the neighbor count, the key being the neighbor count. Look that up and you'll get a function back. And the function will tell you what should happen to the given position. So look this up, get a function, and invoke that function with these arguments. The arguments being the pixel in the frame and the color that we want to change. So this is kind of strangely or poorly written. I suppose I could have, whatever. I could have written it in a different way, but I was, it's the result of kind of changing my mind about how this would work while I was writing it. Let me show you the rules function, the rules dictionary. So the rules dictionary is analogous to what I was showing you in the illustration or the drawing. It has keys that correspond to different neighbor counts. So you have 0 neighbors, you should die, 1 neighbor, you should die, 2 neighbors, you should live, and so on. And these values are functions that I've defined up here that just say what should happen to a pixel if you're going to die. What should happen to a pixel and a color if you're going to die? So what should happen? Just get back to 0. If you're going to live, get back to 255. If you're going to stay, just get back whatever you were originally. Don't change at all. So yeah, that's how the rules thing works. That's how next frame works. Now I can just briefly talk about neighbor count. So we start our result at 0. Xlen and Ylen are just the lengths that we're going to iterate through. X delta and Y delta, we're just going to go between -1 and 2. This is just kind of a shorthand or easy way to write that what we want to do is we want to look at all the adjacent neighbors. So if we are considering this cell right here, we want to start at -1, -1. And here, these are deltas. So if you say your X position is 0, 1, if you say the coordinates of this cell are 1, 1, then the cells we want to consider are -1, -1, -0, -1, +1, +1, -1, excuse me, that doesn't make any sense, +1, -1, and so on. -1, 0, 1, 1, +1, and 1, 0. So this is like +0, -0, +0, +0. Anyway, so that's what these nested loops do. If both of the deltas are 0, that means we are considering the cell that we're actually on. So we won't let that contribute to our neighbor count. But otherwise, we're just going to say if the position mapped by X delta combined with X and Y delta combined with Y, if that position is within the bounds of our array, so we're trying to reach something in our array, then we're going to check and see whether it's alive, in which case we'll return a 1, or dead, in which case we'll return 0. You know, it wouldn't be within the bounds of our array if we were checking something on the edge of the array. So we just wouldn't count anything for these. And so that's how the neighbor count works. It's going to return, is it alive, of the given coordinate. And is it alive is just the check I mentioned before, meaning is it greater than 127 at the given coordinate within the frame. So is the red value greater than 127 at 0, 0, at 0, 1, and so on, is the green value. So all that lets us apply the rules of the game of life in 3 dimensions, essentially, or three separate red, green, blue boards. And what that produces for us, let me see if this will animate. Yeah, so what that produces for us is a kind of, I guess, strange, psychedelic maybe, image of Trump kind of dissolving into a static or a chaotic color. Let's see if we can make it a little bigger. Yeah, so it starts out obviously resembling Trump. Exactly, it's just a picture. And one thing I think is interesting is you can see it pretty quickly switch to just the borders before it starts to dissolve more into the kaleidoscopic kind of madness pattern. And there should be 8 different colors here. You can kind of see, like, I suppose it's like the shapes of the game of life spreading in their different colors in different regions. Some of them are entirely red. A lot of it is mixed. That's the image-based game of life. Personally, I'm very interested in the game of life, and I love, kind of tinkering with it and exploring different ideas or variations of the game of life. If you are too, and you want to see more stuff about the game of life, like button, subscribe, say something in the comments, especially if you have an idea for how to vary the game of life or what you'd like to see with it. Or if you have images that you want to dissolve like this, I'd be happy to share the code or put it somewhere where people can use it. But that's it for me. So thanks for watching. Bye-bye.